Welcome to this next lecture, that is lecture 4 on electrical machines 1, and we have started our discussion on transformer, and we discussed several important concepts which is essential to understand the working principle of transformer. For example, in our last class I told several important things. One is that suppose there are now two coils and we are discussing about ideal transformer. Ideal transformer, that is, these winding resistances are 0 of both the coils. There is no leakage flux and permeability of the core is infinitely large, which means that if you energize this primary coil with a known voltage at a frequency sinusoidal voltage, then the current drawn is vanishingly small. And if that be the case, then there will be phi t, peak value of this phi t is phi max, and this phi being time varying also links this coil and you have induced voltage. Then I told you about the dot marking, these are called dot marking, how to find out the dot markings by applying Lenge's law. So that everything is now in place. One should not be thinking this way, that way. Apply a given voltage at a frequency, RMS voltage of the induced voltage and its polarity with respect to this plus minus, all things are now drawn, polarities, instantaneous polarity plus minus. Then the secondary instantaneous polarity is also this one, and V 1 and E 1 will be same, there is nothing in between. Similarly, V 2 and E 2 will be same, and also we noted that E 2 by E 1, RMS value of the induced voltage is V 2 by V 1 is equal to N 2 by N 1. This is the essential thing of a transformer. Therefore, you can change the level of voltage simply by manipulating the number of turns ratio. Okay. Now, this is the thing, and then in my last class I told you how to draw phasor diagram. You see, magnetizing current with the assumption that there is no leakage flux and mutual flux only. So, this coil to this AC supply, this coil will appear as an inductance. What else? Because no resistance. See, essentially N 1 d phi dt is nothing but L di dt. From your circuit analysis, you know, if time permits we will dwell upon that, but the point is, so if I want to draw the phasor diagram, I will do it like this. This is my applied voltage. Carefully see. The current drawn by this circuit will be 0. Will it be 0? Not really, vanishingly small current. Okay. So, that current will be lagging this by 90 degree, a small current, but that current produces a finite flux phi. Getting, these are the phasors. This flux will induce voltage in the primary coil and E 1 has to be equal to V 1. Therefore, primary coil induced voltage will be like this, also equal to E 1. I told you in some books phi E 1 in the 90 degree, but I know the whole story now. E 1 only, it acts in opposition with supply voltage, but with respect to time they are in phase. When V 1 attains maximum, E 1 attains maximum. So, I will draw like that. Similarly, E 2 will be along the same lines, its length may be different depending upon if n 2 is greater than n 1, it will be above, and this angle will be 90 degree. I m, magnetizing current, is vanishingly small. Achha, now in today's lecture, we will further go. That is, so far the secondary circuit, nothing is connected, except while deciding about dot convention, I told okay, something you connect, very casually I told okay, connect, then the current direction, whether you allow this EMF to act like that. But now today we will see much more deeply what is going to happen if you connect something here. So, I will what I am trying to tell you, imagine that there is some load which is still now open circuited, there is a switch. Our discussion till now with S opened, whatever we discussed with S opened. Now, the question is what happens if I close S? Okay? That is very interesting. Mind you, with S opened, let me write with S opened, open condition, S open condition, what is going to happen? Apply voltage, frequency, flux is created, E1, E2, if you connect a voltmeter, you can measure all the voltages, and this current, if you connect an ammeter, is going to be very close to 0, since it is an ideal transformer, and so on. Achha, when S is open, it is a magnetic circuit, single coil, and MMF acting in this magnetic circuit with S opened, MMF acting is equal to N 1 into this I m, magnetizing current, which is very close to 0, no doubt. Is not, that was the net MMF which was acting, and this MMF created a flux phi. This created this flux phi inside the core, N 1 I m by reluctance, is not, N 1 I m created the flux phi in the core. So, N 1 into this flux, so amount of MMF necessary to create the flux phi is known to me, N 1 into I m. Now, listen carefully what I am telling. You close the switch, imagine you have closed the switch. The moment you close the switch, this coil too will carry current, is not, this coil too, because there is a source of EMF, you have connected an impedance Z 2 here. So, the magnitude of the current will be E 2 by Z 2 and so on. Therefore, to find out what is the flux in the core of the transformer, it looks like that this MMF I have to take, and then net MMF I have to calculate, divided by the reluctance, that will decide the flux. Okay. In fact, that is what is going we have to do, but before that I tell you one thing, that okay, when the S was open, what was the flux? How to tell flux? You tell phi max and frequency. Okay, phi max was fixed, I am writing it many a times, root 2 pi f n1. That was phi max, it was fixed, and this phi max has to be there in order that KVL will be satisfied on the primary loop. Now, what I am telling, whether this switch is opened or closed, the flux in the core cannot change. That is what I am telling. That phi max and its frequency of course will remain same flux must prevail. Why? Because primary has to satisfy the KVL equation, that is V 1 equal to 4.44, root 2 pi is 4.44, f phi max into n 1, V 1 is fixed. So, on the primary winding the KVL is to be satisfied, V 1 equal to E 1. Therefore, phi max cannot change, no matter whether you have connected something on the secondary coil or not. In other words, what I am telling, even if you have connected some load on the secondary side, so that secondary coil is carrying current, then flux, this flux cannot change. What it was, it will remain. Therefore, I will write it whether S is opened or closed, phi, that is core flux, will not change, cannot change. If earlier it was phi max some sin omega t, it will be still phi max sin omega t. S is opened or closed, it does not matter. But then we are slightly perplexed. Second coil is carrying current, primary was initially carrying a very small current. Acha, now I will tell you that way you better you think. Okay, if flux remains same and these two coils are carrying current now, so what will be the net MMF necessary to create that original flux? You must understand this N1 IM when S was open created this flux in the core. What I am telling, with S closed, when both coils carry current, when both coils carry current with S closed, net MMF must be once again N1 into IM, because N1 into IM created this original flux, and I am telling with S closed or opened, flux remains same, it cannot change. Why it cannot change? Because this flux will make the KVL equation valid on the primary side. What was the MMF which created this flux phi? N1 into IM, where from we concluded that when S was opened. So, with S closed, I am once again telling that flux remains same, but both the coils perhaps will carry current. But I am sure the net MMF once again has to be N1 into Im. It cannot be other than that, because net MMF divided by reluctance, reluctance remains same, will decide the flux and flux remains same. Okay. So, let us see what happens, what I mean by this. This is the most interesting part of it. So, this is the thing. So, here what I am telling, we are now discussing this thing Z2. This is my S. And instead of telling that I m is 0, I will tell let magnetizing current is very small, finite. So, initially N 1 into I m is the magnetizing current, magnetizing MMF with S open. Net MMF with S closed must be also N 1 into I m when both the coils carry current. Now, how such a thing can happen? Let us see. Suppose you now connect this switch, it has become a seat of EMF. Therefore, it will deliver some current I 2, RMS value of that current is suppose I 2, instantaneous current. Therefore, secondary coil will create an MMF N 2 into I 2, instantaneous values or N 2 into capital I 2 RMS value of the current. Primary prior to closing of the switch was carrying a current of I m, magnetizing current. Now, when the secondary will carry a current I 2, it will try to create flux. If you see this one, it will try to create flux in the opposite direction, is not? Your thumb rule, it try to create flux in the opposite direction. Therefore, when you close the secondary switch like this, your primary cannot be a idle spectator, mere spectator to this event that you are doing this. What it will do immediately, the moment you try to draw some current through the dot of the secondary of the transformer, it will draw additional current, say I 2 dashed, of such magnitude that N 1 into I 2 dashed is equal to N 2 into I 2. This I 2 dashed is called reflected current. Therefore, I want to draw current from the secondary of the transformer. I know then it has produced an MMF N 2 I 2, which is acting in the anticlockwise direction, it tries to create flux. But I am telling the moment you do that, primary draws extra current. So, what is the primary MMF? N 1 into that original magnetizing current plus I 2 dashed. This will be the total MMF, that is equal to N 1 I m which acts to create flux in this direction, plus N1 I2 dashed. From the dot current is coming out, it also creates flux in this direction, clockwise direction flux. And on this magnetic circuit, apart from these two MMFs, a third fellow occurs, which is N2 I2, or I will write plus, create this way. Therefore, in the earlier case when S was opened, net MMF acting in the magnetic circuit was N1 IM. When you close the switch, what is the net MMF acting in the circuit? Let there be N1 IM, and these two will cancel out, because N2 I2 creates flux in this one and N1 I2 dash creates flux in this one, and if these two are equal, they will cancel out. So, net MMF how much it is acting now? Once again N1 into IM. This is the most crucial point, and this the transformer has to do for all the time. That is why it is true for instantaneous values also. So, what is the thing going on? Initially, the net MMF in the transformer was N1 IM. I am telling with S closed, once again the net MMF has to be N1 IM. Therefore, if secondary delivers a current of MMF N2 I2, let me write here small letters N2 I2, if it delivers a current I2, its MMF. Therefore, this MMF if will be compensated by the primary by drawing additional current I2 dashed over and above IM, such that not any value of I2 dashed of this value. So, that these two MMFs once again balance, and net MMF will be once again N1 into IM. That is why people say the moment you want to draw current or power out of the secondary terminals of a transformer, primary cannot be a mere spectator to this event. The moment you do this, primary will react. It will draw additional current such that N1 through the dot terminals, mind you, through the dot, if you show the current going out, then only these two fluxes will MMF. Therefore, net MMF once again will be N1 IF, these two will cancel out, because from physical directions I know. So, this will be the thing. Later I will tell you about this whole lot of physical way of understanding the thing. There is easier way of understanding that look here, if you draw power output from the secondary of the transformer, primary current must increase. How it can? Because this is the only 2 points where I am pumping power into the system, and you are taking power out of the system between these two. Therefore, if you consume power here, ultimately power has to come from this place here. Therefore, this power must balance. We will discuss about those things later, but I hope you have understood. So, what I am trying to tell, because this is so important a point in understanding the transformer. So, what I told, let me review this, because this is so important. There I connected a switch and a load, is not? I am trying to understand what is going to happen when this switch is closed, because after all you cannot just step up or step down the voltage without connecting, not connecting anything across the secondary. Yeah. have to deliver this power to some load. So, this is the thing. So, initially with S opened, I am concluding that S opened, net MMF acting is N1 into IM. With S closed, once again I am telling, in this case this was also net MMF, secondary current was 0. So, net MMF was this. With S closed, net MMF N1 into IM must be net MMF. Why? Because flux level cannot change, but MMF is contributed by this coil current and its number of turns, this coil current and this number of turns. So, net MMF of the primary coil is N1 IM plus N1 into I2 dashed, and this is in the clockwise direction, flux it creates. Net MMF of the MMF contributed by secondary, if you show this is the current, it is N2 I2 and it creates flux in the opposite direction. Therefore, these two MMFs N1 I2 dashed and N2 I2, if these two things are equal for all the time, mind you I2 is varying sinusoidally, then everything is fine. These two will cancel out. So, if I draw the magnetic circuit like this, suppose magnetic equivalent circuit, it will be, there are two MMFs plus minus N1 IM and here also plus minus N1 I2 dashed. Here is the reluctance of the magnetic circuit and here is another MMF acting in the opposite direction. What is that? N2 I2 and this is I2 dashed. What is the net MMF acting? N1 IM plus N1 I2 dashed minus N2 I2 divided by reluctance. So, net MMF is N1 IM plus N1 I2 dashed minus N2 I2. And this has to be equal to N1 IM. How this can happen? If these two are equal, this must vanish to 0. That is why the moment you want to draw some current I2, primary will immediately react and draw additional current I2 dashed on top of IM, which was vanishingly small, that is fine. So, it will draw a current of IM. So, please go through this particular topic, discuss among yourselves with your friends the arguments put here to conclude that no matter whether the switch is opened or not, flux level in the core of the transformer remains fixed and it is decided by only V1 and F, no matter whether S is closed, S is opened, because the moment S is closed, it will draw current, but flux level in the core has to remain same because it has to satisfy, it has a duty to satisfy the KVL equation on the primary loop. You cannot have circuit KVL is not satisfied. Therefore, it must be E1 and E1 is root 2 pi F phi max N1. So, phi max cannot change. The moment you close, then what happens? Initial MMF was N1IM with S opened. Final net MMF has to be N1IM. If these two are equal, these and these are equal, these two MMFs will cancel each other and flux remains N1IM by reluctance. That was the idea. Please go through it. Hope you have understood. Thank you.